So we have already arrived at this equation or vector equation or matrix. Now, to simplify further the equation, we can rewrite the mass matrix as just this one, the mass matrix times the response acceleration plus the stiffness matrix times the what do you call this, the deformation vector is equal to the dynamic force vector. Well, you know, initially from the two equations derived from using the direct dynamic equilibrium approach, and then from our FBDs, we have a single equation resulting with the mass matrix times the response vector, response acceleration vector plus the stiffness matrix times the deformation vector is equal to the dynamic force vector. If you look closely, this is similar to the SDOF, no? With the mass times acceleration plus the stiffness times the response velocity is equal to the dynamic force. Now, for the undamped free vibration response, undamped free vibration response, the applied dynamic loading is equal to 0. Then the general equation of motion will become the mass matrix times the response acceleration vector plus the stiffness matrix times the deformation vector is equal to 0. Okay, since we have our general equation in this form, we have also our general solution. General solution U is equal to, we have the phi sine of theta plus omega times the time. And the first derivative is just equal to, we have the phi omega, sorry, cosine of theta plus omega t. And then the response acceleration is equal to the negative phi omega squared sine of theta plus omega t. Sorry, what are those variables that are present there? The omega is the natural frequency, our natural frequency. And then the t is the time. The theta is the phase angle. Now, we did not concern with the phase angle because later on this will just be removed. But we have our focus here for the phi. Now, this is our mode shape factor. Okay. So what is the mode shape factor, sir? The mode shape factor describes the shape of the structure under, say, free vibration response. So that is the, later on we're going to sketch the shape of the structure under free vibration response. We'll be getting the mode shape of the structure per floor and then per differing natural frequencies. So let's go back to our general solution. We have the mass matrix times the acceleration that is equal to negative phi omega squared sine of the phase angle plus omega t plus the stiffness matrix times the phi sine of theta plus omega t is equal to 0. Now, if you look closely, the sine theta omega t is common, then we can divide the whole equation with sine omega t. Then we are left with the mass matrix. And here we have the negative omega squared. And then we also have our mode shape factor. Then we have our phi vector plus the stiffness matrix is equal to 0. So we just rewrite this in the form stiffness matrix. We have also our phi vector here. Minus omega squared times the mass matrix. And then we have our mode shape factor, or the phi vector, is equal to the null vector. Now, since we arrived with this one, we can rewrite this in the form. Actually, this is in the form uh, eigenvalue equation. Now, the solution for the eigenequation, we have here our eigenvector. Call this our eigenvector. And we have here our eigenvalue. Now, it is very important to get first the stiffness matrix, and then we have also our mass matrix, and then we should arrive in this form. Now, having arrived with this form, our next step would be getting the determinant of the stiffness matrix minus omega squared times the mass matrix is equal to 0. So, in order for us to understand these steps, no, we are going to make use the formulation, we can use the equations of motion that we have just formulated here, and then we can understand the mode shape. Let's have our first example. So we have here is the structure supported by four concrete columns per floor model as shown. We have a structure, and then it is very important to read the equation. Well, we have four concrete columns, square columns. Please take note that this may not be always the case. No, at times we may give another value, like let's say there are six concrete square columns, so on and so forth. It might be a concrete, it might be a steel column. So here in this specific problem, we have a four concrete column for the structure. And then the compressive strength F prime C of the structural member is 21 megapascal. We have also the dimension of the column as 300 millimeters by 300 millimeters. And then we have the corresponding height per floor. So we have H1 is equal to 1.25, H2 is equal to 1.333, H3 is equal to the 4 meters. The H1 here corresponds to the height of the first floor. The H2 corresponds to the height of the column carrying the second floor. And then the H3 corresponds also to the height of the column carrying the third floor. And then as you can see here in the figure, we have the mass of the first floor is equal to 5,000 kilograms. The mass of the second floor is 2,500 kilograms. And then we have the mass of the third floor, or the topmost floor, is equal to 1,250 kilograms. And then another given condition is we have here the motion factor of the topmost floor is equal to 1.0. Take note of this word. We have the topmost floor, the motion is 1.0. So we need you need to take note of these details, because at times problem may give you that the mochi factor for the second floor is 1.0, or probably on the first floor is 1.0. So for this example, the mochi factor of the topmost floor is equal to 0. Now, you're asked to find the stiffness of one column per floor and an equivalent stiffness per floor. So why there are differing stiffness per column per floor? Remember, the equation for the stiffness K is equal to 12 EI over H cubed. Now, we'll have a single stiffness and equivalent stiffness for the whole structure per floor if the height of the columns are just the same all throughout the floor. Now, in this specific example, the height of the first floor, second floor, and third floor columns are varying. Therefore, we will have a differing value of stiffness per bar. And then next is we are asked to find the natural frequencies, the omega, and the time period. And then lastly, thirdly, we are asked to find the mode shape factors per floor. This is the phi. And then lastly, we're going to sketch the mode shape or that and then the total mode shape as well. So let's start first with our very first step. So what are the steps no, in calculating the mode shape factor for an MDUF system? First is you need to get the stiffness matrix and as well the mass matrix. Then you need to get this vector, the stiffness matrix minus omega squared times the mass matrix, and then get the determinant of that one. And then afterwards, you'll be able to calculate the natural frequencies, so on and so forth. And then afterwards, you'll be calculating the mode shape factors. Then lastly, after able to calculate the mode shape factors, you'll be able to sketch the mode shapes. Okay, so we'll start our calculation in the next video.